Friends, I, Digvijay Charan, welcome all of you in this episode. In this episode, I will discuss about iron-carbon equilibrium diagram in detail, giving focus on industrial application. The equilibrium diagram means it indicates the phases formed during slow cooling or slow heating. If the cooling or heating is fast, these phases will not form, but some other phases will form, which is not topic of discussion at this moment. The diagram you can watch on the screen. On x-axis, it is carbon percentage ranging from 0 up to 6.67%. This is carbon ranging from 0 up to 6.67%. On y-axis, it is temperature in centigrade and also temperature in Fahrenheit. Now, first I will define few important temperatures which are called critical temperatures. A0 is a critical temperature of 210 degrees centigrade. This is A0 temperature. This temperature is A0 temperature of 210 degrees centigrade. Now 210 degrees centigrade is the Curie temperature of cementite. Curie temperature of a material means a temperature above which it is paramagnetic and below which it is ferromagnetic. Now ferromagnetic means the material can easily get magnetized and has high ability of retaining magnetism. Now you come to A1 temperature. A1 temperature is 723 degrees centigrade. This I will discuss later. Now come to A2 critical temperature, that is 768 degrees centigrade. It is the temperature above which ferrite is paramagnetic and below which ferrite is ferromagnetic. So 768 degrees centigrade is the Curie temperature of ferrite. So below this temperature, ferrite is ferromagnetic till ambient temperature. Hence, at 200 degrees centigrade and below, ferrite and cementite both are ferromagnetic. So, carbon steel or cast iron can be easily magnetized below 210 degrees centigrade. Now I will discuss about phase change. If we draw a vertical line at 0.8% carbon, it is all liquid state. The moment it cools down, it will pass through certain area. Whichever area it will pass through, the phases shown there will form. Ultimately, it will come down to austenite. Here is delta ferrite and liquid, here is delta ferrite, here delta ferrite and austenite and liquid. Ultimately come down to austenite. Now if we take 0.8% carbon steel from liquid state, it will cool down, it will come to austenite and liquid, then austenite. If we take 1.2% carbon steel, it will cool down from liquid to austenite and liquid and then austenite. So in the carbon steel region, I mean up to 2% carbon, I told earlier in the earlier video that carbon steel is having maximum carbon 2%. So in having any carbon percentage in the carbon steel region, if it is cooled down from liquid state, ultimately it will form austenite. Now austenite with 0.2% carbon, when it will be cooled, it will pass through this curve. This curve is called A3 curve. which connects 910 degrees centigrade with A1 temperature. The moment austenite is cooled through this curve, here it will form austenite and ferrite. If it is further cooled, then below A1 temperature, it will form ferrite and cementite. Now austenite with 0.8% carbon, when it will be cooled at A1 temperature and below, it will form ferrite and cementite. Now perlite shown here is a combination of ferrite and cementite. If you take 1.2% carbon, if it will cool down from liquid, it will form austenite and liquid, then austenite. And after austenite, when it will cool down, it will pass through this curve, ACM curve, which is joining 1143 degrees centigrade to A1 line. When it will pass through this curve, it will form austenite and cementite. When it will be further cooled below 723 degrees centigrade, it will form ferrite and cementite. So in the entire carbon steel region, you select any carbon percentage below A1 temperature, it will form ferrite and cementite. So this is the importance of A1 temperature. Now we come to cast iron. In cast iron, suppose you take 3% carbon, it will cool down from liquid to austenite and liquid, austenite and cementite, then below A1 ferrite and cementite. If you take 4.3% carbon, it will cool down from liquid to 1143 degrees centigrade, below which it is austenite and cementite, and further if it is cooled down below A1 temperature, it will be ferrite and cementite. Here lead-borite shown is a combination of ferrite and cementite. So perlite and lead-borite both are having inside ferrite and cementite. Now if you take carbon more than 4.3% but lower than 6.67%, when it cooled from liquid state to liquid plus cementite, then if it is cooled below 1143 degrees centigrade, it will form austenite and cementite. It will further cooled below A1 temperature, it will make ferrite and cementite. So in any carbon alloy, whether carbon steel or cast iron, any carbon percentage you select, below A1 temperature, it will form ferrite and cementite. So that is the importance of A1 temperature. Now, this point, 0.8% carbon is called eutectoid point, and steel having 100% perlite is called eutectoid steel. Similarly, 4.3% carbon is eutectic point, and cast iron having 4.3% is called eutectic cast iron having 100% lead-borite. Now here, if carbon is lower than 0.8%, it is called hypoeutectoid steel written here. If carbon is more than 0.8%, it is called hypereutectoid steel shown here by name. So I repeat, if carbon is lower than 0.8, it is called hypoeutectoid steel. If carbon is more than 0.8, it is called hypereutectoid steel. Similarly, in cast iron area, if carbon is less than 4.3%, it is called hypoeutectic cast iron, and if it is more than 4.3%, it is called hypereutectic cast iron. So eutectic cast iron has 100% lead-borite, and eutectoid steel is 100% perlite. So this is how here you have four areas: hypoeutectoid, hypereutectoid, hypoeutectic, and hypereutectic. Now as you move from left to right, extreme left is ferrite, 100% ferrite, and extreme right is vertical line showing cementite. As you move from left to right, I mean from lower carbon to higher carbon percentage, the ferrite content will decrease and cementite concentration will increase. I mean by weight fraction, the proportion of ferrite will decrease and proportion of cementite will increase. It is possible mathematically very much to calculate that if you select any carbon percentage in any of the four areas, one can calculate how much fraction will be ferrite and how much fraction will be cementite. In next episode, I will discuss about that formula. Now, for industrial application, we can divide carbon steel into three categories. First one is mild steel, that is called low carbon steel. It is having carbon percent up to 0.25. Most of the mechanical items used in industry are fabricated out of mild steel due to its high ductility. Examples are plate, pipe, tube, etc. Next category is medium carbon steel. It has carbon content between 0.25% to 0.6%. This category of steel is used as tool steels, such as spanners used to tighten the bolts and nuts. Medium carbon steel is used as railway tracks, train wheels, crankshaft, gears, or machinery parts. Please note, in the railway industry, the rails over which trains run are made of 0.8% carbon steel, that is eutectoid steel having 100% perlite. Now third category is high carbon steel. It is the carbon steel having carbon percentage between 0.6% and 2%. In industry, high carbon steel is used for very limited applications such as knives, chains, etc. So in next episode I will explain the formula to calculate the weight fraction of ferrite and cementite in any iron carbon alloy. Friends, if you like this video, please subscribe the channel, share the video and like the video. Thanks.